Hello, and welcome to the video for 9.2b, Transformations of Exponential Functions. Our objective for today is that I can apply dilations to exponential functions, and I can apply reflections to exponential functions. So, example 6, vertical dilations of exponential functions. In this case, we have an a term that is out in the front of our exponent, and it is being multiplied by the power. And so whatever this a term is out in front here is going to affect our graph. Now, if that a term, if the absolute value of it is greater than 1, that is going to stretch. That is going to stretch out our graph and make it taller. We're going to stretch it out vertically, so our steps are going to get bigger from one spot to the next because we're multiplying by something else that is greater than 1. So our steps are going to get larger. If our a term is between 0 and 1, the absolute value of it is between 0 and 1, that is a compression. Meaning it is going to be shrunk down vertically. We're pressing it down. We are not taking as big of a jump because that value between 0 and 1 is a fraction. We are cutting something in half or in a quarter or in a third, and that is going to mean we're not going to grow quite as rapidly. So let's look at some examples. The parent function for this first one is y equals 2 to the x, and we see that graphed for us. We've worked with this one before yesterday. And now we need to graph y equals 1/2 to the times 2 to the x. Well, first off, just looking at our formula, this is a fraction. It is between 0 and 1. The absolute value is between 0 and 1. So that is going to be a compression. Okay, so we have a compression of 1/2. So how is this actually going to translate out into the work that we're doing? Well, we need to take each of our values and multiply it by 1/2. So we have 1, 2, 3, 4, we have 5 values shown for 2 to the x power, going from an x of -1 to an x of +3, right? So -1, so 2 to the negative first power, that's 1/2, or sorry, 2 to the negative first power is 1/2, and then we multiply it by 1/2 again, and it's going to be 1/4. So it's going to be a little bit lower. 2 to the 0 power is, anything to the 0 power is 1. 1 times 1/2, well, now we're at 0.5. 2 to the first power is 2 times 1/2 is 1. 2 to the second power is 4 times 1/2 is 2. 2 to the third power is 8 times 1/2 is 4. 2 to the fourth power is 16, divided by 2 is 8. So what you'll see is our graph still has the same asymptote, but you'll see that it's rising slower, right? We have a division of 2. Essentially, we're taking away a power of 1 on our multiplication. So you can see how this has changed a little bit. We're not having a direct shift from left to right per se. We are having a vertical change, right? We're cutting this in half. All right, our next example here, we've got y equals 1/2 to the x power is our parent function. And our new function is y equals 3 times 1/2 to the x power. And so you'll see, again, we have 5 points, and these are kind of familiar points because we're still dealing with like a variation on 2 to the x power. So 1/2 to the x, if we have a negative value, we flip that fraction and it becomes 2 over 1. So, 1/2 to the negative third power is 8. 1/2 to the negative second power is 4, to the negative first power is 2, to the 0 power is 1, to the first power is 1/2, and you see it decreasing there. So now what we're going to do is we are going to multiply each of these values by 3. right? Because that's what we have there. So this is going to be a stretch of 3. So we're going to stretch it out vertically by 3, or by a factor of 3. So if we do x to the first power, right? 1/2 to the first power is 1/2. 1/2 times 3 is 3/2. So that's right here in between 1 and 2. Okay. 1/2 to the 0 power is 1, times 3 is 3. 1/2 to the negative first power is 2. 2 times 3 is 6. 1/2 to the negative second power would be positive 4. 4 times 3 is 12. And so we are immediately off the graph here. And so we can see what's happened. We've shifted. The graph is it's stretched, but we still have the same asymptote. And I did an approximation of where that 12 is going to be above the graph. But we can see we are stretching this out. My intervals, my jumps between them are getting bigger as I go step by step, as I go from the parent function compared with our new function. All right, the next two problems are U-tries. I want you to go ahead and do those on your own and then check your work against mine. All right, so our first one, we have a parent function graphed. It is y equals 3 to the x power. And we are graphing a 2 times 3 to the x power. So our value there, that 2, that means we are going to stretch by 2. So we're going to double everything. So it's going to grow quicker. So we've got that negative first power. So that would be 1/3 times 2 is going to be 2/3. We have anything to the 0 power is 1 times 2 is 2. We have to the first power, 3 to the first power is 3, times 2 is 6. And then 3 to the second power is 9, times 2 is 18, which is going to be way off the graph. So again, our asymptote stays the same. But we see how quickly our graph is growing compared with our original parent function. All right, and our next one. So we've got y equals 3 to the x power again. That is our parent function. And we are going to be multiplying it by a factor of 1/3. And that is going to be a compression of 1/3. Okay, so essentially we are dividing our growth by 3. So our graph is going to get closer to the asymptote. So if we have our first point here, 3 to the negative first, which is 1/3, times 1/3 again is 1/9. So that's going to be way, way closer to the 0 line. We've got anything to the 0 power is 1 times 1/3. So that's times 1/3, or to 1/3. 3 to the first power is 3, times 1/3 is 1. 3 to the second power is 9, times 1/3 is 3. 3 to the third power is 27. 27 divided by 3 is 9. And so we see how this graph shapes out. Again, our asymptote stays the same, and you see the growth that we have. So we've compressed it. We've pulled all these points down by a factor of 3. All right, now let's go to example 8. Example 8, describe dilations of exponential functions. So since 2000, the solar PV, or photovoltaic capacity in the world has been growing exponentially. It can be approximated by the function c of x equals 0.897 times 1.46 to the x power, where c of x is the solar photovoltaic capacity in gigawatts. X is the number of years since 2000. Describe the dilation in the function as it is related to the parent function f of x equals 1.46 to the x power. Describe what the dilation means in the context of this function. So first off, we have 0.897. So that's a compression of 0.897. And what is this starting? What does this do for us, right? So if we can think about it, anything to the 0 power is 1. So if we are looking at a factor of 1, right, we're multiplying 0.897 by 1 in year 0, in the year 2000. We're multiplying it by 1. So what does that tell us about this 0.897? It tells us that our starting capacity is going to be 0.897 gigawatts, right? 0.897 gigawatts is, in the year 2000, the starting capacity for photovoltaic solar cells in the in the world. All right. So that is our starting amount. That's where we're moving from. And then every year after that, we are multiplying by 1.46 to identify what our next amount is. So we compressed it, but it is, the growth rate is there, but that is where we had to compress it to start, because that was the amount that we had in the initial amounts of photovoltaic capacity in the year 2000. All right, letter B. Fish stocking refers to the process of raising fish in hatcheries and then releasing them into waterways to increase existing populations or to create a new population. Ideally, when new fish are added, they reproduce and their population grows exponentially. Suppose the population of a certain fish in a new pond can be modeled by the function p of x is equal to 50 times 1.5 to the x power, where x is the generation. Describe the dilation as it relates to the parent function f of x equals 1.5 to the x power. Describe what the dilation means in the context of this function. So we have the 50 there. So we have a stretch of 50. Okay, so we're stretching it by 50. We're making this graph bigger. But what does this tell us about the context? Well, again, let's think about that year 0, right? That generation 0. Nothing has changed, but we're multiplying it by 50. That is going to show us that we are starting with 50 fish initially in the pond. Right? Our starting population is 50. We put 50 fish into that pond, and every generation we multiply it by 1.5. So it increases by 50% every generation, right? And we'd be able to substitute, figure out how many generations have passed, and assuming that that relationship has continued, we would be able to say how many fish there are in the pond. All right, so now you guys are going to go ahead and do the U-try problem. There are 2 of them, C and D. Go ahead and try those now, and then check your work against mine. So letter C, we have water hyacinths. They are an invasive plant that is not native to Ghost Lake in Africa. The growth can be modeled with the function y equals 1,000 times 2 to the x power, where y is the area covered by hyacinths after x years. Describe the dilation in the function as it is related to the parent function y equals 2 to the x power. Describe what the dilation means in the context of the function. So we have the dilation. It's a 1,000 there. So what are we doing? We are stretching by 1,000. Okay, and what does this mean in the original context of the equation? We are starting with an area of 1,000. And I can't add in any units because we weren't given any specific units in this. But really what this says is, let's say it's square feet or square miles or whatever it may be. You are starting with 1,000, let's say, square feet. And then every single year, that area doubles. That is an insane growth rate. So it is a significant issue as it's an invasive species. That means it is affecting the rest of the ecosystem and threatening native plants. All right, so we're going to go to letter D. Mold can grow exponentially or extremely quickly on food items. In the experiment using gelatin and chicken bouillon as a growth medium, a group of students grew mold that was modeled by the equation m equals 50 times 3 to the d power, where m is the area of the mold in square millimeters after d days. Describe the dilation in the function as it relates to the parent function m equals 3 to the d power. Describe what this dilation means in the context of this function. So, our dilation is 50. So we have a stretch of 50. And what does it mean? We start with, so our initial mold is 50 square millimeters of mold. So we start with 50 square millimeters, and then we grow from there. So we're going to go on to number 10 now. Example 10 is vertical reflections of exponential functions. So when we have a negative sign out here, and I want to be on my highlight tool, that is telling us a negative a value means we are reflecting that transformation. We are going to have a vertical reflection. So we are flipping it across the x-axis. So in our example here, right? So all of these are going to be a vertical reflection. So we have each one of these has a vertical reflection. We are flipping it across the x-axis. So if we picture this, 2 to the 0 power is 1 times negative 1 is negative 1. 2 to the second power is 2, or 2 to the second power, or sorry, 2 to the first power is 2, multiplied by negative 1 is negative 2. We have 2 to the second power is 4, inverse is negative 4. 2 to the third power is 8, we flip it to 8. So we are going to get the same asymptote, but we are now the opposite. We're going downward. Okay. On our next one here, we have y equals 1/2 to the x is the original parent function, and we see an example of that there. We're going to graph y equals negative 1/2 to the x power. All right, so we are going to flip these essentially. So at negative 3, 8, we're now going to be at negative 3, negative 8. So I'll put my point in down there. Negative 2 to the and 4 is going to now be negative 2, negative 4. Negative 1 and 2 becomes negative 1 and negative 2. 0 and 1 is now 0, negative 1. 1 and 1/2 is now negative, or 1 and negative 1/2. So all we're doing is we are flipping the axis, or flipping across our y-axis, x-axis. And everything is going to have the same relationship, same distance away from that axis. And you can go ahead and do the math on it, right? 1/2 to the negative third power is going to give you positive 8, and then you take the negative sign on it, it's now negative 8. So you're able to graph this out. 2 U-try problems for you, and then we're going to check your work against mine. So our parent function, y equals 3 to the x. Our graph, is y equals negative 3 to the x. So we are going to be flipping this across our x-axis. And so negative 1 and 1/3 will be at negative 1/3. Our y value is 1, so we're going to be at negative 1. Our y value is at 3, so we're going to be at negative 3. Our y value is at 9, so we're going to be at negative 9. Again, we're approaching the same asymptote. We're not shifting left or right with this. A negative term, and in this case, we just have a negative sign in front. It's not, we're not stretching or compressing any because right now we've just worked with negative signs. But if we had a negative coefficient there, you'd have a stretch or a compression as well as flipping the orientation of it. Our last one here, y equals 1/3 to the x power is our parent function. Y equals negative 1/3 to the x power is our graph that we're going to make. And so I know that I need to be flipping everything across the x-axis. So that point at 1/3 becomes a point at negative 1/3. My point at 1 is now negative 1. My point at 3 is now negative 3. My point at 9 is now negative 9. And so again, we have a graph that's rising and approaching that asymptote of y equals 0. Okay, so key reflections for today. When we have something out in front, it can be a compression or a stretch. So we could be going from we could be shrinking it towards the x or the y axis or x axis, or we could be stretching it out and elongating the graph. And then if it's a negative sign, we are flipping it to the bottom 2 quadrants of our graph instead. If you have any questions, please bring them to class tomorrow. Otherwise, I hope you have a great day.